In this video, I just want to mention the existence of a transform of a periodic function right here, and I want to talk about where this formula comes from. In your book, they do have some other derivation for this, but I don't think it's very much fun. So we're going to do kind of what I think is a neat derivation for this formula right here. Now, just to give you an idea of what all this notation means, t is actually the period of this periodic function. So down here, you'll notice I just made up a random periodic function. It repeats. T is the period of that function, and we're calling just this one little piece, the piece that repeats, f sub p of t. So if you're using this formula and you have a periodic function, what you do is you almost do kind of like a miniature Laplace transform, but on just this little piece, this f sub p of t right here, and you just integrate from 0 to t instead of from 0 to infinity. You divide that by 1 minus e to the s times whatever the period is, and that's your Laplace transform. What I want to do is give you an idea of where this formula comes from. So when we have a function and it's new to us, we don't know how to find a Laplace transform of it, what do? Hopefully by now you know the answer to that question is we use the definition of a Laplace transform. Well, we have ourselves a discontinuous function here, so how are we going to integrate it? The answer to that question is we actually have to split up the integral into several pieces. Well, we know that from 0 to t, the function has a name. We call it f sub p of t. What we're going to have here is actually an infinite series of integrals split up from 0 to t, t to 2t, and so on. Now let's look at this integral from t to 2t. If our function from 0 to t was f sub p of t, then the piece of the function from t to 2t that we're integrating here is the same function, it's just shifted to the right by t units. That's capital T units, of course. So we can put that piece of the function right here into this integral. The next piece of the function is just going to be f sub p shifted to the right by 2t units. So the infinite series of integrals that we get when we use the integral definition of Laplace transform is going to look something like this. Now all I'm going to do is I'm just going to rewrite this. I'm going to rewrite each one of these integrals with a U-substitution. So in this integral here, the U-substitution is u is little t minus big T. Big T, of course, is just a constant that we're going to know for, when we're given this function. This integral here is going to have U-substitution, u is t minus 2t, and so on. Okay, now what happens when we actually perform this U-substitution? So all I did is I replaced all of my little t's with u's, and my integrals turn out to look something like this. Now my question is, what are the limits on these new integrals? Well, the old limits were on little t. So in this first integral, if little t is big T, then that means that u is going to be 0, big T minus big T, just 0. And if little t is 2 big T, that means that u is going to be 2t minus t, which is just t. And what you'll find is all of the limits on all of these integrals are just going to be 0 to t. Now for consistency, I really should do a U-substitution, but u just equals t in this integral here. And I'm going to replace my t's with u's. And the only reason I do that is so all of our integrals kind of start to look the same. Now I'm just going to use a little bit of algebra on these integrals here. Now all I did was use the old algebra trick about similar bases, adding powers, to split up our exponential in this term, and in this term, and in every term after it. Then you'll notice that this e to the negative st doesn't have a u in it, so it's a constant with respect to the variable of integration, so you can pull it out of that integral. The same is true here. We can pull this out of the integral. Now look what we have here. We have the same integral in every single one of these terms. So we can factor that integral out of each one of these terms, and we're left with an infinite series inside of these parentheses. I, of course, added this next term in. All we have to do at this point is a little bit of algebra and recognize that we know this infinite series. This is actually just a pretty basic power series, this one right here, and we know that whenever x is absolute value less than 1, that this series adds up to that right there. So what we're left with in the parentheses is just 1 over 1 minus e to the negative st. And that's it. I think that is just the entry in our Laplace transform table. Anyway, I think that's a pretty cool derivation because you get to use your knowledge of infinite series. Now, as far as using this formula goes to find the Laplace transform of a periodic function, Capital T is a known value. It's just a constant. So you're going to plug whatever your period is in for capital T. And you're just going to do this integral on the first part of the periodic function from 0 to the period. Once you do that integral, you're finished finding the Laplace transform. All you have to do is copy down 1 minus e to the negative s times whatever the period is. Okay, so video quiz time. I just want you to find the Laplace transform of this function right here. So notice it's the same function that I drew above, except I've actually given you values, so you can do the integral. Okay, good luck. I'll see you in class.